Okay, so the first question, which of the following are measures of efficiency for a propulsion system? And we'll just pull the results up. So 57% of you said eta propulsive, same for specific thrust so far. 52% said eta thermal, 52% said specific impulse. I love how they're coming in groups. 35% said eta propeller and specific fuel consumption. And I love it when they don't all fit on. And 35% said thrust specific fuel consumption. Okay. So let's talk about etas. That nice Greek letter is the letter we use for efficiency in propulsion systems. So anytime you see an eta, and it's a sensible word after that that goes with your propulsion system, be it propulsive, thermal, or propeller, it is an efficiency. Now, not all propulsion systems have a propeller, right? So we'll talk about these in turn. So, what is eta propulsive? And that is basically the measure of how much thrust power we get out. So thrust power is literally the thrust equation times velocity, so TV, so m dot Vj minus V infinity times V infinity. It's how much thrust power we get out for a given amount change in kinetic energy, delta kinetic energy. The more kinetic energy it takes to get that thrust power, the less efficient we have, the lower the eta propulsive is. Eta thermal is literally how much delta kinetic energy we get out in our thrust tube for the amount of chemical or electrical or nuclear energy we put in. So the fuel flow rate times the heating value of that fuel. So if we get more kinetic energy per fuel thing, we are higher eta thermal. Okay, so those are two straightforward ones. Propeller efficiency obviously only applies in the case where we have a propeller, and it's just how good we are at converting shaft power, that turny bit, into thrust power. So obviously, eta propeller will be part of eta propulsive for those types of systems. Okay. We also have specific thrust, specific impulse, and our specific fuel consumptions. Specific fuel consumption, and therefore specific impulse, are a function of eta propulsive and eta thermal. They are a function for how much thrust, not thrust power, but thrust or power we get out of our system for the amount of fuel energy we put in, right? So they are also measures of efficiency. So therefore, the only one that isn't is specific thrust. It is a measure of how much thrust we get for how much mass flow. Not energy, just mass flow. And we'll talk about that relationship here in a little bit. Okay. Now, we're going to talk more about eta propeller. I don't expect you to know a whole lot more than just this next question. Propeller efficiency is a function of what? Engine power, advance ratio, or wind. Now, obviously, the size, the propeller we want is going to be a function for a given aircraft. It's going to be a function of a lot of things. Engine power, how we're going to operate. But its efficiency, how good it is at converting shaft power to thrust power, isn't really a function directly of either of those two things. It's a function of that combination of the shape of your propeller, how much it has to turn the flow, and how much the inflow is. And we call that advance ratio. It literally is how much we would expect our propeller to advance if we turned it into the equivalent fluid. Not the fluid moving by, it pulling itself through. And each propeller shape will have an optimal advance ratio. If we fly faster, it will become less efficient. than the optimal, we fly slower. It becomes less efficient. I don't expect you to calculate advanced ratio. It's just to know that your propeller efficiency is a function of advance ratio, and advance ratio is a function of the shape of your propeller and the inflow velocity. How do we maximize it over a range? We use variable pitch propellers, what are known as constant speed. They turn always at the same speed, they just change their pitch to maximize what they're trying to get. A to PR is always going to be less than or equal to 1 because we're never perfect at converting shaft power into thrust power. What do we generate because we're not perfect? What's that sign? How do we know, you and I, sitting on the ground, sitting in the aircraft, know that there's a loss there? Yeah?
We hear the sound of
the propeller. Yep, you hear noise, because noise is a loss. If you hear just a low rumble, a constant rumble, that's jet noise. That's not so much a loss at the propeller, but that sound of that propeller, that's literally telling you that inefficiency exists. Okay. Any questions so far? No. Let's start with the next one. So we'll do gas turbines and jet engines here. Give you a second. So the first question, before we get into, and it relates mostly to we talk about it mostly with jet engines and gas turbine engines, but it relates to all of our propulsion system. What happens as specific thrust increases to efficiency? Does efficiency increase or decrease? Now, specific thrust is quite literally the amount of thrust we get per unit of mass flow. That could be mass flow of our propellant in a rocket. It could be mass flow of our air in our gas turbine jet engine. Now, we typically just use air mass flow because in a jet engine, the fuel mass flow is much, much smaller. It's orders of magnitude smaller, so we don't worry about it. So specific thrust is T over m dot. So it is literally that difference in the velocities. Now, remember we said propulsive efficiency is maximized when that difference is closest to 0 because we get very little change in both kinetic energy and thrust. So we maximize our m dot, which means, of course, if that's a big number, specific thrust is a smaller number. So as a rule, all else remaining equal, specific thrust, as it goes up, our efficiency goes down. So in broad classes of propulsion systems, those with lower specific thrust are more efficient. Now, this doesn't account for thermal efficiency, so you can have all sorts of thermodynamic or other losses in the back end that play in that. But things like piston props, turboshaft props are more efficient overall than turbojets and then rockets. Another thing is it turns out, in general, the reliability and life of our propulsion system goes up as our specific thrust goes down. It's not perfect. Gas turbine engines, for lots of reasons, are more reliable and have better life than piston engines. Mainly the forces, the non-reciprocating forces help you a lot. But rocket engines have very, very short lives. They're measured in minutes or few hours versus a modern turbofan, high bypass ratio turbofan, we measure time on wing in tens of thousands of hours. We have some aircraft that have been operating at 50,000 hours who have never where the engine has never been removed. It's that reliable, that much life. But in general, as our specific thrust goes up, our efficiency goes down. Okay. So let's now talk about jet propulsion and gas turbine propulsion. So, which is the simplest type of gas turbine engine? Is it a turbojet, a piston engine, a turbofan, turboprop, turboshaft, ramjet, or scramjet? Now, this brings us back to our definitions. A gas turbine engine is an engine that literally uses gas flow through a compressor, a combustor, a heater, and a turbine to get energy out. It does not and is not related to our propulsion method. So a gas turbine, its working fluid is its combusting or heating fluid, and we use a turbine. So anything probably here with turbo is a gas turbine. A jet engine is a different thing. A jet engine is any engine where the working fluid, that fluid we ran through the turbine, is what we use to propel it. So in this, a turbojet, a turbofan, a turboprop, these to some extent, ramjets and scramjets are all jet engines. But a ramjet and scramjet, do they have a turbine? No. So they're not gas turbine engines. Piston engine, does it have a turbine automatically? Now, you can. What do we call it if we put a turbine in the exhaust and then use it in the front end? Yeah.
Are you talking about turbo compounding?
Well, you can do, yeah, turbo compound. Well, turbo compounding is a little bit more, but just any type of turbo supercharger, because there's more to turbo compounding than just having a turbo supercharger, is yeah, but that would be part of the gas flow. You could consider it a pseudo gas turbine, but we don't have to have turbo supercharging. Though we can have mechanical supercharging or no supercharging. Turbo compounding involves also exhaust flow and using it for thrust and stuff like that. Okay? So technically our turbojet will be our simplest because each of these has something more complex. We have power extraction turbines that go off-takes either to a prop or out somewhere else, and then we have that fan on the front in a turbofan. So they're more complex. Okay. What is the simplest type of jet engine? Ramjet, turboshaft, turboprop, turbofan, solid rocket, piston prop, or cryogenic rocket? And as we said, a ramjet has no moving parts. It follows, the suck, squeeze, bang, blow principle by doing it all with the energy naturally contained in the moving flow. So it's just a shaped tube. A scramjet's the same thing. The only difference is in a ramjet, we slow our flow down to subsonic speeds before it goes through the combustor, if it wasn't subsonic. A scramjet, which is supersonic combustion ramjet, we don't do that. So that's a really simple thing. It's just a shaped tube. So absolutely, that's a correct answer for a jet engine. Obviously, a turboshaft is not a jet engine. These are hybrid mixed. But the odd one is our solid rocket. The solid rocket is literally the rocket equivalent of a ramjet. It's a tube with a nozzle. The only difference between it and a ramjet is instead of getting our oxidizer from the atmosphere, it's stored in our propellant on board. So they are equally valid answers for the simplest type. Okay? We'll pause that. Any questions? Man, you guys know it all. So let's just get on to space propulsion while we're on it. This one has a few more questions. 5 in this one. And we'll talk about space propulsion here in a minute. So a jet engine is any engine where the working fluid, that is anything where you have a fluid that you do work or add heat to or energy to electrically, is your propelling fluid. So all of our rocket engines are technically jet engines. They use a jet as its propellant. Turbo compound engines actually have a jet value to the thrust. The other great one was the P-51 Mustang was notorious. They used a ram-compressed air that went through the radiator for the liquid-cooled engine and then had a variable area nozzle to create thrust from that. So that technically, that component was a jet. So it was primarily a piston prop-powered aircraft. Huh? So basically, they compressed the air from the ram, added heat through the radiator, and then vented it through a nozzle. It was a pretty crude, not very efficient ramjet, but it was more efficient than just dumping the waste heat overboard without getting anything out of it. So 22 of you have responded. We can get started on this one. Okay, so which of the following is a monopropellant rocket? Is it a hydrazine rocket, an H2O2 rocket, MMH-N2O4, RP1 LOX, and LH2 LOX? 60 and 64% of you said H2O2 and hydrazine. 20% said these two, and 16% said MMH-N2O4. Monopropellant rocket is a rocket that does not have a separate fuel and oxidizer. It's just one chemical that we cause to disassociate into a gas, which raises the pressure and temperature, and then we vent that for thrust. So we need an unstable chemical. Often then we may heat it up just a little bit to get that reaction started or pass it over a catalyst. The most famous of these is hydrazine. It's nice, it's storable, it's relatively stable at room temperature, so it lasts forever. But if we heat it just a little bit, or even better, pass it over a catalyst, it reacts, it disassociates, we get the two reactant gases, and we get energy release, and we can make a rocket out of it. We've been using hydrazine since the dawn of the space age. It replaced alcohol pretty early on. One of the problems with hydrazine is it's toxic. It's not that toxic. You and I can handle it. We use it in things. They use it in all sorts of medical stuff. But chronically, it's not good. It has environmental damage. Anybody know what H2O2 is? Yes?
Hydrogen peroxide.
Yeah, hydrogen peroxide. It is less stable than hydrazine. It's also, because it's got extra oxygen, somewhat reactive. It is an oxidizer on its own. It is, however, a bit less environmentally damaging because it naturally just goes to free oxygen and water. So it is the idea of a green storable propellant. Now, to keep it, we actually have to keep it chilled because room temperature, especially on a hot day, it would disassociate. It would too quickly. We wouldn't store it well. But if we keep it chilled to, say, 5 degrees C, it's pretty good. And then we can just heat it up a little bit, pass it over a catalyst. It disassociates. We get water vapor and oxygen. It can eject those. Okay? So why are we interested in H2O2? Well, hydrogene's great, but when we store it, there are risks to the people that maintain it, the environment around it. So a number of years ago, there was a program in the US to look at making their ICBMs more environmentally friendly. We all laugh at that, but then you realize the purpose of an ICBM is to sit there ready to be used, but never be used. So most of them sit in a silo for a long time, then they take them apart, they have to maintain them. They're notorious for occasionally killing the people that maintain them, or maybe you drop a wrench and bad things happen. So the idea on the Minuteman was to replace the upper stage, the post-boost vehicle that decides where to drop off the entry vehicles, which is currently hydrazine, or was then hydrazine powered, with an H2O2 system. Yes?
Wait, but is that a question
Yeah, that's the purpose of an ICBM.
But they would have to be used in situations like, say,
Yes, but that's a failure of the purpose of an ICBM. It means that you've failed. You've achieved total war, basically wiping out civilization. The purpose of having an ICBM is to prevent you from wiping out civilization. It's one of these weird, strange things. Mutually assured destruction versus the light. Okay, so let's talk about these. Obviously, with two things like that, that's a bipropellant system. Okay, the first one here, so those of you, the 65 and 62 now, are correct. Those of you, what the other ones? Okay, let's start with RP1. Anybody know what RP1 is? Yeah. Yeah, so RP1 is a synthetic kerosene. and we use it rocket propellant. It's the American term, so that's why you see it a lot. Obviously, the Russians and other countries use different terms. We tend to use synthetic kerosenes for rockets because we can get much higher quality, much higher reliability of our fuel. RP is from a mil spec in the US. Anybody imagine what the two letters at the front of the jet fuel are? Yeah.
JP.
Yep, jet propellant. You have 5, 6, 7, 8, all of these different ones. They are different specs. Now, LOX, liquid oxygen. So the nice thing about RP, about kerosene, is it stores really well. It's a room temperature thing. It's stable. It doesn't react very much. It's definitely better than petrol. LOX, on the other hand, is cryogenic, so we have to keep it very cold. So this is a semi-cryogenic rocket. One is normal room temperature, one is not, so it's not storable, so it boils off. LOX is really good because it's one of the best oxidizers. It's also relatively easy to handle. Yes, it is very reactive, it is corrosive, it will catch fire, but it's not that bad compared to some other things. LH2. What's that? Yeah, liquid hydrogen. So liquid hydrogen is the ideal fuel in terms of efficiency for a chemical rocket. You can't get any lighter than hydrogen. Your exhaust is all water vapor, which is very light. So we use it for upper stages. The problem is it's very hard to store for any length of time. It boils off quite readily. And compressing it, the joke is it's like pushing ping pong balls around. It's not easy to compress. If I need an injection head pressure of 200, 300 bar, that's really hard to achieve with liquid hydrogen, but it's very efficient. There is one chemical combination for a rocket that's more efficient than LH2 LOX. Anybody know what the oxidizer would have to be? Yeah. Fluorine. We tend not to use it because fluorine itself is toxic and hydrofluoric acid is really nasty. Water vapor is pretty benign comparatively. Okay, so we have a semi-cryogenic and a cryogenic. This bottom one is an example of a storable hypergolic propellant. So storable means it can sit there for a long period of time. The propellants and the oxidizer are quite stable. Hypergolic is nice because all you have to do is mix the two and they ignite. They combust automatically. We don't need an igniter. We don't need to add energy to initiate the reaction. So MMH is a derivative of hydrazine. It's more stable. So therefore we can't use it as a monopropellant, but it stores better. M in this is monomethylhydrazine, MMH. The other common one in this combination is UDMH, which is unsymmetric dimethylhydrazine. And N2O4 is our oxidizer. That's dinitrogen tetroxide or nitrogen tetroxide. These are highly toxic. And I like to say the rockets that use them, so Proton, the old Titan rockets used a hydrazine derivative. So Proton uses unsymmetric UDMH and N2O4. The Titan systems, like they use for Gemini, and the US used for launching larger space vehicles, so the Voyager probes, spy satellites were launched them. They used what was called Aerozine 50, which was a combination of UDMH and pure hydrazine. MMH and N2O4 is what the orbital maneuvering system, the bigger rocket, maneuvering rockets on shuttle used, and the like. They're highly toxic. There was, when they launched the Cassini mission, a bunch of people protested. They chained themselves to the launch pad before the launch because the Cassini space probe had a radiothermoelectric generator, so a chunk of plutonium or thorium or whatever, and they were afraid that if the rocket blew up, it would contaminate everything. What no one failed to realize was that actually far more deadly was the fuel on the rocket, and there was a Titan launch that failed, released a cloud of UDMH and N2O4 into the atmosphere, and it just so happened the wind that day was not its normal westerly. It was slack, but they were worried it would come and be an easterly wind and blow that cloud back over Florida. And they were trying to figure out how they were going to evacuate 2.5 million people. Because if it settled on any one of those areas, it would have been catastrophic. So Orlando, for instance, like Disney World, was one of the things they thought they might have to evacuate. So we like them because they're storable, they're easy to use. We use them for upper stages, especially ones that we have to coast for a long time. Upper stages where we don't have that, we'll use RP or hydrogen. Okay. What is the basic relationship between ISP and TSFC? Is it an inverse, they're identical, or they're totally unrelated? And almost all of you got it right that it is the inverse. So TSFC in consistent units will be kilograms of fuel per Newton of thrust per second. And ISP is in seconds. So obviously we have to invert it to get seconds. The big difference there is if we have TSFC in consistent units, you need g, the acceleration due to gravity, the local g. If you use inconsistent units in TSFC, which is very common, so that's kilograms mass per kilogram force per time, then it is just the inversion and the conversion between hours and seconds. So that means a more efficient rocket has a higher ISP, and a more efficient engine has a lower TSFC. A TSFC of 1 kilogram per hour, which is pretty crap. Keep in mind, most of the aircraft that are flying around today at cruise will be around 0.5 for their TSFC. That's the equivalent of an ISP of 3,600 seconds. So 0.5 is 7,200 seconds. The RS-25, the Space Shuttle main engine, is one of the most efficient chemical rockets ever built. It has an ISP in vacuum of about 470 seconds. You're talking more than 10 times the efficiency out of a modern gas turbine. Okay? And that's just because the specific thrust is so low. Okay. Chemical rockets are a type of jet engine, true or false? Remember, jet engines are about the propelling fluid relative to the working fluid. Rockets are, all of it is propelling fluid. We use the propellant, we mix it, we can burn it, and we eject it. And it is therefore our working fluid, our combusting fluid, and our propelling fluid. True, yes. It is exactly the same as the propelling fluid. Okay? The working fluid and the combusting fluid, if they're the same, what type of engine do we have? The working and combusting fluid are the same. That is what type of engine? So it's the way we extract mechanical power out of it. So an internal combustion engine is one where the working and combusting fluid are the same. If they're different, i.e. like steam turbines and stuff like that, that's an external combustion engine. Okay. Which of the below are types of electrical space propulsion systems? Ion engines, resistojets, Hall effect thrusters, nuclear rockets, or chemical rockets. And most of you got these right, or at least some of them right. The top three are. So an electrical propulsion system is one where instead of using chemical stored energy or other thermal energy, we use electrical energy to increase the energy, internal energy of the propellant, and then we eject it. I.e., therefore, a chemical rocket is definitely not that. Nuclear is a bit of a mix. There are different types of nuclear. The first one is nuclear thermal, which is where we have a reactor core or a decomposing bit of material that's radioactively decomposing. It heats the fluid, and we use that. That would not be an electric propulsion system. We also have ones where we generate electricity from our nuclear reactions, either the decomposition or critical mass, and then we use that to excite and accelerate those flows, and those would be electric propulsion. One of the nice things about nuclear thermal and chemical rockets is they are inherently thrust limited, which means they're really good for things like getting off a planet, accelerating quickly. These are power limited, so we typically, when we talk about electric propulsion systems, talk about thrust in micro and millinewtons versus kilonewtons or meganewtons for these things. Yes? Okay, so when we're talking about air-breathing engines, we don't carry our oxidizer around. So our propellant is a mixture of the atmosphere we suck in, m dot A, mass flow of air, and m dot F, the fuel. Obviously, in the case of a rocket, chemical rocket, we just have propellant. It's just m dot. Okay? Well, they're both inputs. It's just one is from the atmosphere and one is from the fuel tanks. Okay. Solid rocket motors are bipropellant systems. True or false? And the answer is true. Solid rocket motors use a fuel and an oxidizer. They are just bound together in a binder. In fact, often our binder is our fuel. Now, oxidizer, what do they typically use? So most solid rocket motors that you and I deal with, the powerful, the fuel, it will be something like HTPB, and I don't remember what that stands for. It's like polybutadiene or something is the PB. And then the oxidizer will be ammonium perchlorate. And it's mixed in that rubber binder. The nice thing about HTPB is it is a rubber, so it is naturally a binder. The other one that was commonly used is PBAN, which is another polybutadiene. And they have different properties and reasons why we've switched back and forth. Also, for really, really high thrust motors, like on, say, a missile that needs to accelerate quickly, we will often dope it with aluminium or magnesium to increase the temperature quickly, even though it decreases the efficiency. But solid rocket motors are bipropellant. They carry their own separate chemical oxidizer and fuel. Okay? Is that the last of those? Any questions? What are white and red fuming nitric acids used today? Not so much, mainly because they also decompose and react. We've replaced them with N2O4 as our primary. The original hypergolic rockets were alcohol and nitric acid. So V2 used alcohol. And we just get better ISP, better storage out of these things. A number of years ago, we were putting together a hybrid rocket lab, and we were looking at what chemicals and stuff to use. And we ended up doing the classic hybrid rocket where you use rubber as the fuel and nitrous oxide, laughing gas, as the oxidizer. But just was curious about what you could buy. And on the university's procurement system, you could get hydrazine and red fuming nitric acid, so we could have built a nice rocket, but I didn't try to order that. I didn't want to deal with the paperwork. How do you keep a scramjet lit at supersonic speed? The answer is very carefully. So the issue with the scramjet isn't actually keeping it lit. Getting it lit's an issue in the first place. It will burn. The problem is that to get that energy out, we need the recombination of the fuel components. So what happens is, if we've got a liquid hydrogen system, we have to take that H2 and the O2 in the air, decompose them into H ions and oxygen ions, and then recombine them back into water vapor. And that's a multi-step process. It goes through hydrogen peroxide, OH ions, and then down to water vapor. And that's an easy one. That's quick. That's the simplest chemical reaction we have. We know all the steps of that reaction. But remember, we're moving very quickly. So if that doesn't happen fast enough, that flow will be outside the nozzle by the time it recombines. No good to us. It'll nice and glow blue. So anytime you see a blue flame out of a rocket, that's OH and O combining to water. That's what that blue flame is. If we use a hydrocarbon, like kerosene, it's a much more complex reaction. And that recombination goes from free carbon and oxygen and hydrogen ions to carbon monoxide, CO, and hydrogen peroxide, and then down to CO2 and H2O. It's those last steps, the OH to H2O and the CO to CO2, that we get most of our energy out. If you see a flame coming out of a rocket like that and it's orange, that's carbon monoxide combining with oxygen to get CO2. All of that is just waste heat. And that's the challenge. In designing a scramjet, you need to make sure it happens inside that combustion tube before it gets to the nozzle and gets out. And that's really the challenge with scramjets. And that's what took so long. And that's why it was also the first scramjets that we proved could produce net thrust were hydrogen powered. And then you have to work down because it's much more complex for hydrocarbon. We use special fuels that we try to decompose before we inject them. So you have less time. It's all about recombination, not about the initial decomposing for those types of things. Okay? Okay, I've got one last poll, and this one's not related to this topic. It won't be on the exam or anything, but it is relevant to aviation. It was stimulated by the email that went out yesterday. What's the difference between regulation and guidance? And it's free text. And this is very important because next year, especially when we talk about design and future stuff, you will see stuff, and when you read the documents, there will be regulations and there will be guidance. And how do you treat them and what do you do and what's the question? Just in the interest of time, we'll see what some of the answers are that people have. Regulation is something that must be adhered to. Regulations have rules that have to be followed. Guidance or recommendation. Regulations are enforced, but guidance isn't. Guidance is optional, and the like. So yeah, you've got it basically. So regulations, the UK is not actually a regulation country. Here we use statutory instruments, and they're slightly different. Secondary legislation, as it's called, but it's effectively the same thing. The US and the EU are all regulation-based things. Regulations are law. They must be followed. So anytime you see the word must, that will tie back to a regulation. Or in the case, if you're an applicant trying to get your aircraft or your engine approved, it may say shall do X, meaning you have to demonstrate that. That's the regulation. In the US, when we talk about civil aviation, civil space, we talk about the FARs, Federal Aviation Regulations, hence it's law. That actually, they're a subset of a much bigger thing called the Code of Federal Regulations. The fundamental difference between what we have orders and statutory instruments in the UK and regulations in the EU and the US has to do with how we promulgate them, we create them. A statutory instrument is created by a minister. It is inherently a political process. Regulations are semi-apolitical. There's a whole process where they have to justify, there's a choice for review, and you and I can challenge a regulation based on the way it was put together, not just whether it was legal in the first place. But it's slightly different. Guidance in aviation and aerospace specifically, but in general, is a means of helping you meet the regulation. It's suggestions. The thing about guidance, it is neither necessary nor always sufficient to meet the law. I can follow the guidance to a T and still be breaking the law, or I can ignore the guidance altogether and still meet the law. Now, the challenge is, if the CIA issues you guidance and you choose not to follow it, you have a much higher burden of proof that you are doing things correctly. In the US, where we have those regulations and guidance and all of that, you'll see what's called alternate means of compliance and special conditions. And that's where a company like a Boeing or an Airbus or a Rolls-Royce or GE, they say, you know what? We've got a better way of meeting the regulation and the intent of the regulation. Here's how we're going to do it. And the FAA will accept it or reject it and the like. Standards are a bit different. Unlike guidance, if you follow a standard that's been accepted by the regulator, you know you have met the law. You will meet the regulation. You don't have to follow a standard. That would be a regulation standard. If it is not a regulation-based standard, if the regulation doesn't say follow the standard, you can do other ways. So in aviation, the most common standardized thing we have is fuel, jet fuel. It's an ASTM standard. The nice thing is if you meet the ASTM standard, you know that your fuel is approved for every aircraft flying that uses jet fuel, that type of fuel. If you go outside the standard, you have to certify your fuel on every aircraft engine combination you want it to be used on. That is prohibitive. We need a consistent supply. So that's why we use standards. So guidance usually says should, regulations say must. Okay? And that's only the difference. That's the big difference. It was just because of the wording that came out in the email and the notice yesterday about wearing masks, and they confused guidance and regulations like they always do. But in aviation, we can't confuse that. You will get yourselves in trouble. So guidance just helps you. It's usually the path of least resistance. I generally recommend following the guidance in aviation, but it isn't always necessary. I mean, a classic one was, for a while there, the CAA guidance said, as long as it was below 120 meters in altitude above the ground and within 400 meters of the pilot for UAVs, you were good. The problem was the regulation says, the Air Navigation Order says, that you must be able to see your UAV and see and avoid other traffic at all times. For a small UAV at 400 meters out, there's no way you could have done that. So you would have been following the guidance, but you would have been well outside the law because of the way the law was. So that was a good example. It's now been strengthened in some ways, and the 120 meters is now a hard limit when it wasn't before. Okay. Any other questions before we run away? Remember, next week is Artifacts of Import. Again, anybody who see if you can find the thing in the video that's now incorrect, no longer true, or true in the full sense, and we'll talk about that. Question, didn't the SR-71 have a combination of turbo ramjet? Yeah, so it had what was called a variable cycle engine, and at high speeds, they would take a certain percentage of the flow and bypass it around the compressor and combustor and turbine and straight into the afterburner. There are a couple of other designs that were doing that, but that was the one that saw the most service. Do I have one at home? No, my house is nowhere near big enough, and they are a mess. Keep in mind the fuel for the SR-71 is pretty nasty stuff, because to fly at those speeds, make sure it combusts in the time, and was temperature stable and all of that, it's a really nasty chemical combination. Okay? Anything else? Otherwise, I will see you next Tuesday.